So this first question, you can do it.
Yes, sir.
How do you do it? What is electric field at point?
4K lambda by R.
No. How do you do it? Just tell me the steps.
We have to see that electric field due to that positive wire at that P and net electric field at P, sir, due to these both
What is
wires.
electric field due to the positive wire?
K lambda by R. 2K lambda by R, sorry.
Okay. So this is an infinite wire, no? So how do you get that formula?
Yes, sir. We have seen, no, sir, in class.
Yeah, that's by using Gauss law. Okay. How do you take a Gaussian cylinder? That's coming out of the Earth's surface. From there you can find this. Okay. And electric field is minus lambda. So will it be in the same direction?
That is also to yes, sir.
Okay. So both will add.
Towards I cap. Yes, sir.
So this plus it will be into the plane of paper. Okay? No. Towards right.
I cap.
Right, towards right.
Yes, sir.
This one secondly. This is also very trivial.
Symmetrical charge distribution. Rho is what, sir? Is it density or something else?
What?
Rho means
Directly charge
density.
Charge density.
Charge density. Okay, charge by volume.
This is standard notation, no? Nothing.
Okay, charged sphere is present inside the uncharged sphere. Am I right, sir?
Exactly. No.
Then the charge density is 0, no, sir?
It's outside.
Then
This is capital R. Outside there is no charge. Outside the charge is 0. Outside, as a function of R, so rho of R is given.
it's a solid sphere. Hollow sphere means there won't be any charge inside the sphere, no, sir?
Yeah. Charge is there everywhere inside. R less than R. Because rho is given as function of R, so you have to find electric field at a distance R. You will find electric field at this point R.
So how did you get that first expression, sir?
I not have got the answer. I made some mistake. So what is the mistake here? R square, no. Okay. R square. This is R raised to the power cube, right? R raised to the cube. R square. You have to close the door. The room is very high. Okay, this step is clear. Your mic is off. Your mic is off. Your mic is off.
I went to close the door.
So this one, so this is the thing, right? So whatever charge is present inside, that will contribute to the electric field. If you have a spherical shell, For the point outside of the spherical shell, it will act as a point charge inside, right? At the center. You know that concept, right? Suppose I have a spherical shell of charge.
Yes, sir.
For point outside the electric field, to find the electric field here outside, I have to assume this full charge is located in the center. Okay, and for point inside, electric field is 0.
Yes, sir.
Whatever, to find electric field at this point, that is due to all the spherical shells. This I can consider as a lot of spherical shells, right? Okay, so for all these spherical shells, this point is outside of the spherical shells. So all the spherical shells, I can consider as it is a point charge located in the center. Okay, so all the charges present inside, I can consider all the charges at the center point and find electric field due to that. And for the spherical shells which are outside, the electric field will be 0. The electric field inside the thing is 0, right here.
Yes, sir.
Only the charge is present inside R, this radius, that will contribute to the electric field at R.
Yes, sir.
How to find Q inside this one, that is called Q of R. Okay, that is 4 pi R square D square, R square dr, volume of the spherical shell into the density. This is clear, no? This step.
Volume means 4/3 pi R cube only, no, sir.
So, volume is to find
That
this.
is area, no, sir. Surface area.
These are standard concepts. To find the total charge inside the spherical shell, I'll take a small spherical shell, right? What is volume of the spherical shell? Volume of the shell is 4 pi R square dr, right? Volume of the spherical shell. Spherical shell of thickness dr. What is it? Your voice is not clear. I can't hear you. So to find the volume, total charge in this one, I have to take a thin spherical shell here.
Yes, sir.
Volume of the shell is 4 pi r square into dr. The dr is the thickness of the shell.
So volume of the shell is 4 by 3 pi r cube only, no, sir. That is surface area of the sphere only, no, sir. 4 pi r square.
I'm just asking the volume of the shell. Volume of the shell is only this volume, not the internal points. Internal points will not count. So there is this surface area that is 4 pi r square into this thickness. This is a standard integral concept, no? This you are studying in maths also, application of integrals. How will you find the volume of the spherical shell? See, what is the surface area of this inner sphere? 4 pi r square, right? So, what is the surface area of the outer sphere?
4 pi that capital R square.
No, 4 pi r plus dr square. R plus dr.
And that is only
4 pi r plus dr whole square.
Okay, I took it as
Okay.
capital R.
So the difference is not much. So approximately the area of these two spherical spheres are same, which is 4 pi r square. So that area into this thickness will give you the volume.
Oh, okay.
This is a standard concept of integral. Okay, so the volume of the spherical shell is 4 pi r square into dr. The total charge in the spherical shell is rho into 4 pi r square dr. Is that clear? It is actually dq. This is dq of this shell. Okay.
Yes, sir.
Okay. So that if you integrate from r equal to 0 to that r equal to r, I'll get the total volume.
So what is the unit of dr, sir? It is meter only, no? It has unit, no dr.
Same as r.
Okay, fine.
This if I integrate from 0 to r, I'll get the total charge inside small r. That's what I need, right?
Yes, sir.
So once I get
Yes,
that,
sir.
so that integration, if you do it properly, I made some small mistake. Okay, r cube by 3 minus r raised to the power 4 by 4 r. Okay. Once I know that q, I have to do k, that is into q by r square. So this divided by r square. So r cube will become r, and r raised to the power 4 will become r square. Okay, so k is 1 by 4 pi epsilon naught. So if you 4 by 4 pi will cancel, so it will become rho naught by epsilon naught into this one. That is r by 3 minus r cube. So r by 3 minus r square by 4r is there in everything. Okay, so rho by epsilon naught is the correct answer.
Yes, sir.
So in this expression, if I put small r equal to 0, okay, the electric field should become 0 because it's the center, which is inside of all spherical shells. The electric field at the center is like that inside center point is inside of all spherical shells, right? And electric field inside a spherical shell is 0. So electric field at the center should be 0. Is that correct? The mic is off.
Sir?
Electric field at the center should be 0, right?
Yes, sir.
Okay, so that's what you get from this expression. R equal to 0. Okay, electric field at the center is 0. And if R is very large, infinity, capital R is very large.
Then
R is variable, but if electric field, okay, like R is R, capital R is fixed, R is a variable. So if you put R equal to infinity, okay, it becomes infinity minus infinity. It's not determinate. Okay, then you have to do use L'Hopital's rule. right? Because can you do that? Okay.
Yes, sir.
No, it's not. You cannot do that. It's not infinity by infinity. It's infinity. W is try infinity by infinity. It is infinity minus infinity. Okay, leave it. Because you cannot determine it. It's infinity minus infinity. From this you cannot find out. But if you find the total charge of the sphere, I can find by using Coulomb's law. Okay, that's not part of the question. Now it's clear?
Yes. Yes, sir. Yes, sir.
It's also a standard question only. Okay, in figure 2, concentric spherical shells R and R, inner shell with charge Q and outer shell is uncharged. The amount of energy dissipated when two shells are connected via S. Yeah, so the initial condition is the inner one has got capital Q. Okay. So after connecting, what will happen?
Some charge will go from inner sphere to outer sphere. So.
Yeah. So after that, so you have to find the. So you can.
Until they have same potential.
Yeah. So you can think this is a capacitor. So first. Connect these two. So after connecting,
energy dissipated means.
So initial energy or initial energy minus final energy. So once you connect it, how will the charge get distributed?
Until both the spheres have equal potentials. Q by 3 and 2Q by 3.
Okay, potential with respect to what? Potential.
Inner shell will have the charge of 2Q by 3. Sorry. Oh my god. Which one do? Okay, Q2. Outer shell will have the charge of 2Q by 3 and inner shell will have the charge of Q by 3. So.
Okay. So, and what is the capacitance of a spherical condenser? Suppose I have a spherical condenser, right? We have a charge Q here. What is the capacitance of it? It's 4 pi epsilon naught R, right? You don't know the formula?
No, sir.
Radius. This radius is E. Capacitance of this thing is 4 pi epsilon naught E, right? Okay, then let me skip this one. I'll come back to it. Okay, this one, 8 drops, 1 meter. I charge this one. I merge into one droplet, find its potential. Yeah. So basically, you have to know the expression for capacitance of a spherical conductor.
Wait, sir, I'll check in my last year notes. 1 minute. Appa phone 999.
Yeah, it is 4 pi epsilon naught r only. What I said is correct. This one, just a spherical conductor. Okay, so
Eight times 4/3 pi. Q equal to 4/3 pi.
we have a spherical charge distribution of
No, r is equal to 2.
4 pi epsilon naught A. So here you have to have two situations. The first one is each of them are there. Okay, so
At its surface or what, sir? Find its potential. Potential on its surface or inside or outside. You didn't mention anything.
it is a solid conductor, the charge will go to the surface only. So liquid is a conductor, so charge will go to the surface. And radius is 1 mm in the first case. And charge of each one is
0.006 picocoulomb.
okay. And this final situation is it's related to one big droplet. Okay. It will have some radius, say let's call it capital R. But the charge will be 8, no? So 8 times 0, 6 picocoulomb. So
Two
charges are known. So initial energy is Q square by 2C 1C. The final energy is Q square by 2C. Let me get it.
So we have direct formula now, sir. K/Q by R potential equal to.
You don't have to find potential. Why do you want to find potential? Potential. Okay.
They're asking find its potential only, no, sir.
Yeah. Okay. This is the previous question. So potential is Q by C.
Oh, K/Q by R. K/Q by capital R. Can I type it like that?
Yeah, Q is the total,
Yes, sir.
and you have to find the final radius.
This 2 millimeter.
How do you get that?
Volume, you know, sir. 8 into that 4/3 pi R cube is equal to pi R. 4/3 pi R dash cube. We'll get it as
So it is 2 times R1, right? Yeah, 2 millimeters.
okay.
So what is the value?
Nine into 10⁻⁹ only, no, sir. That K value.
Yeah.
I'm getting as 1.8, sir. Not the right one. 9.3, sir. Okay. 9.3, sir. 27. Okay. (27 into 10⁻⁻) minus 3.027. I took wrong value. 66, it's not 6.
Got it? Your mic is off. What answer?
No. How did you get us to 2.4?
No, this expression is correct, no? Voltage is Q by C. Potential
Yes, sir.
C is 4 pi epsilon naught R here. And Q is 8 into 0.066 into 10 raised to minus 12. And 4 pi epsilon naught is 9 10 raised to 9 divided by 2R. Okay, so 10 raised to minus 3 will cancel this one. Okay, so
yes, sir.
9s are 72, and this is 0.033. 2 will cancel with this one. Okay, so this is 7.2 into 0.33. Is approximately 1/3 of 7 or 7.2. So it is 3 2s are 6 and then 12. So 3 4s are 12. So approximately 2.4. 2.4 is the answer.
8, 7, 52, okay. 9, 6, 72. 2 is 16, 23. Yes, sir. 2.376. But how did you get this formula, sir?
Which one?
We didn't derive this formula in capacitance.
No, you don't have to do it. See, capacitance is voltage is Q by C, no? Q equal to C into V for a capacitor.
No, sir, that C is equal to 4 pi epsilon naught A. How did you get that one?
Oh, this you have to use it. Otherwise, it will be difficult to. This is a formula. If you have a spherical capacitor, okay, of radius E, then it is 4 pi epsilon naught. This is a derivation. So you don't have to.
What if there are two spells, shell inside a shell? Then what is the net capacitance? Those stuffs we didn't see, sir.
That's a different formula. This for a single spherical shell.
Okay, sir. And
okay, that's a separate formula. Those things should be there in that aligned model, no?
no, my last year notes, but I have to check.
I can put this in your folder also. These are aligned notes. See this one, isolated sphere. Okay, capacitance is 4 pi epsilon naught R, where R is radius, and this is spherical capacitor. This is a spherical shell or a sphere. Both it will be same because even if it's a solid sphere, it's a conductor. So the thing will move to the surface. Okay. In that case, this is the capacitance. Suppose it's a non-conductor and there is a volume distribution of charge, then this is not valid. This is for a spherical shell of charge. This is a spherical capacitor where the charge is plus Q and minus Q. Okay. In that case, the capacitance is this one. 4 pi epsilon naught into R1 R2 divided by R divided by R2 minus R1. This is okay, these are different cases. Again, it's plus Q and minus Q, but this guy is zero potential. Capacitance. Okay, here I summarize this one. This is a normal capacitor. Okay, where one will be plus Q, other minus Q. Okay, so this is the formula. Here, this is a special thing where we have earth the inner sphere. So the charges here will be again, is it plus Q and minus Q? Plus Q minus Q. Okay, outside there is one more charge. See, this is a normal spherical capacitor. I'm saying normal because there will be plus Q and minus Q. Okay, there is no this thing. But here I'm not sure. Here minus Q plus Q is here. But outer surface, does it have a charge? Looks like they will have a charge. So you want this study material?
No, sir, I can't understand. How will I study without understanding?
No, this is Allen material only. It's for NEET. So it is Akash would also covered this thing. We not looked at it. So these things are formulas. You have to use it because you cannot derive these things. So, but you should know when it should apply. It should be applicable.
But I should understand that concept, sir. At least for once.
Long time back, not now. The basic idea to derive this thing is you have to find the potential of this spherical this one. Okay, once you know the potential of this spherical shell, you know, right? This is by Gauss law.
Yes, sir.
Okay, once you know the voltage, then you can find. So this is a derivation, just two-step derivation.
Okay, this one, okay, easy, simple.
For this one, you have to, all the electric field will be between these two only. Okay, because whatever electric field lines come out from plus Q will end in minus Q. So since the charge is same, plus Q and minus Q, electric field outside will be 0. And inside here also will be 0. So the electric field is only between these 2 points. And this electric field is a function of R by Gauss law. Okay, so you know electric field as a function of R. So you know the potential difference between these two by integrating E dot dr. Potential difference is E dot dr. So from there you get the potential difference between these two. So once you know the potential difference, you can find the capacitance. Capacitance is Q by V. So from this you will get this one, this formula. So similarly, you have to find the electric field here. So the potential of this one, the potential of the capacitor is the potential between these two. So you have to find the potential of this outer sphere. So that you can find by integrating. Okay. This is a theoretical question. A conducting sphere of radius A of charge Q is placed constantly inside a spherical shell of charge radius B. B is Earth. Choose the correct statements. Okay, the field at a distance R from C. Okay, so the situation here will be the plus Q at the inner charge in the sphere.
Inside that electric field will be 0 only, no, sir, at point C.
Plus Q charge is put to this inner one. So here there will be plus Q and here there will be minus Q. Okay, so the electric field lines will be between these two. Here the electric field will be 0 and here the electric field will be 0.
Potential at a distance of R.
Okay, the option 1 is definitely true.
Second one, sir, I think wrong answer. Incorrect statement.
Incorrect. Then you have to mark it in different ways. So this is true. The potential difference between A and B, potential distance R from C, where R is between A and B. Okay. The potential distance R from C.
Sir, but potential of B is 0 only, no, sir.
The potential of B is 0.
Then option C should be Q by 4 pi epsilon naught B only, no? Then M minus 1 minus 1 by A minus 1 by B.
This thing is valid between A to B, right? Okay, so in this thing, if I put R equal to B, this should give me 0. So obviously, this thing is false. Because this is not a correct expression for the potential. Because this is valid up to B, right? So even less than B, it's just less than B.
Sir, it is greater than A, no, sir. It is like a point charge, no? Potential for a point charge. So Q by 4 pi epsilon naught small r plus Q by 4 pi epsilon naught small b. It is between the spheres. We have to find that potential.
That is true for an electric field. Okay.
For potential also same thing only, sir. We have seen, no, sir, that graph.
Okay, so if you want to find a regressive, you have to find electric field as a function of R. Okay, so potential at any point R. So I know the electric field at this point, right? So I can integrate from here to here. Integral E of R.
So we have direct formula, no, sir. Why do you have to integrate? Shell B is here. So only shell B has to contribute to the potential.
Nothing like that. That is valid only for finding the electric field, not the potential. Okay, so one thing is the electric field, sorry, the potential at point B is 0. Okay, so the potential at this point, and the electric field is only between these two. So the electric field at just B minus, okay, should also be 0. So if you put R equal to B, it should be approximately 0. Okay, here if you put R equal to B, it is 0. Okay, so this is definitely a wrong statement.
So that they have mentioned, no, R is less than B and greater than A. It is correct only, no? Q by 4 pi epsilon naught. Or it is like a potential for point charge.
No, that's only for finding electric field. How many shall I tell you?
No, you told me for potential also.
No.
You check your notes, sir.
That's a mistake then.
No.
This is true. This is true. And B is false. Okay.
So C is how do you say it is true? Potential for B is 0 only, no?
So what? This is
So
0.
the potential difference.
So this is potential at A. So this is actually potential at A, which is same as VAB. Okay. So the rigorous way to find is find ER, that is K into Q by R. Okay. So to find the potential difference between A and B, integral EdR from R equal to E to B. So E is KQ. 1 by R is ln R, no? So if you integrate this one, it's 1 by R. So KQ to 1 by E minus 1 by B. That's what is here. Okay. And if you have to find potential at this in between point, the limits of integral will change from R to B. So when I put from R to B, it will become 1 by R minus 1 by B. These are all standard derivations. This one is standard.
So 1 by R only, you take it as 1 ln. So then why again took integral of ln? Integral of 1 by A only ln A, sir.
Hold on, I made a mistake.
If you differentiate ln only, you get 1 by A.
Yeah. There is a mistake here. It should be ln.
Then it is ln A minus ln B. It is ln A by B. That's what I told you.
Yeah. After integrating, it's ln.
If it is unearthed means then what you said is correct, sir. Option B is incorrect. But if it is earthed, no. So only shell B will contribute to the potential. V due to A is 1 by 4 pi epsilon naught into R.
So once I know potential between A and B, the potential, yeah. Okay, shall we move to the next one?
We didn't find the answer, no, sir. Did they make mistake in question?
Yeah, this is ln. The question is ln is missing. Okay.
No, they should have given without that earthing.
No.
If it is not earthed mean, then option B is incorrect statement. Since it is earthed, option B is correct, sir, but option C and D only wrong.
Option B is not correct. To find potential at point C, Okay, this is the correct expression.
So that is correct if it is unearthed, sir.
Who said? To find
So
the
if potential is zero only, no, sir. It's alone.
see, to find the potential here, you have to find the work done from moving from infinity to that point. No, that is the definition of potential at a point. This infinity.
So you just make clear that shell B will contribute to potential at point A or not. That alone.
There is nothing less. Yeah, it will contribute. See, potential decided by the electric field. Potential is integral E dot dr. No.
But they have earthed it, no?
So what? There will be charge here. The other thing means potential. Potential is here zero. This one means charge is zero here. There is some charge on this outer sphere.
Okay, fine. All right.
Okay, so whatever is the work done from infinity to this point, so that will depend. There is no electric field here. The electric field is only between these two. Okay, so this value of the electric field here depends on to find that we can use this Gauss law, or we can find the electric field at this point is due to only the charge which is charge.
So earthing means charge will go to earth only, no, sir.
No,
Potential will become zero.
until the potential of this thing becomes zero.
Okay, fine.
Okay, so there is a spherical capacitor. My God, I think he has made a mistake. Just a minute. Capacitance of a spherical capacitor. Sorry. It's 1 by R only. There is no law. See, this electric field is 1 by R square. No. All silly mistakes. The electric field is 1 by R square. Okay. So it is 1 by R only. There is no law. Your mic is off.
Yes, sir, 1 by R. We have seen the formula and you forgot it. In your notes only you have given.
So 1 by R square integral is 1 by R. Okay. So we'll get these two. So this is the basic thing you have to find out. The electric field at a distance R is 1 by R square. Okay. So using that.
Then we'll get us as 1 by B minus 1 by A.
No, it's minus.
Okay, minus sign you have included.
So this is the expression for potential at a distance R. So in this thing, if you put, yeah, this is the correct expression. So that you'll get from this one. So obviously this is wrong. When this is correct, this is wrong. Because both are same thing. Okay, one of them is correct. So this is correct. So this is wrong. Okay, you revise after that. I'll send you this GNT file. Okay, so the method of finding this potential is you have to find the electric field as a function of R. So the electric field at this in between point will come only from the charges present inside. Okay, only here you can use the concept that this thing is like a point charge at the center. So once I know the electric field is as a function of R, to find the potential at any point, I'll do the integral from infinity to that point. There is no electric field outside, so this integral from outer this thing B to that R. So the limits are from B to R. So when I put the limit, I get R and B. So integral 1 by R square, so it's 1 by R. This one, electron of mass ME initially at rest moves to a certain distance in uniform relativity in time t1. The proton of mass MP initially at rest takes time t2 to move through the electric field. Neglecting effect. Oh, this is also a trivial question. So the acceleration. What is the answer here? Your mic is off.
They didn't mention about that electric field, the direction and how that electron moves also.
No, whatever is true for electron is same for true for proton. You can assume something. Same is valid for both electron and proton. Initially at rest, right? So both are starting at rest. So the time is what? How will you find this time?
Using that kinematics equation on the size.
Yeah. So will the time be same? Will the time be same? Yes or no? Suppose I take two masses. No. Okay, why will it be?
Because the electron and proton charge is different, no?
Oh.
So one will be experiencing opposing force and one will be experiencing attracting force. The time will vary.
No, but what about the...
Which is experiencing attractive force that will move faster.
Okay, electron is at rest. No. How do you know it's attract? See, what if electron is getting attracted towards positive plate, then proton will get attracted towards negative plate, no?
But the electric field direction, force will be opposite to that electric field direction.
Yeah, they will. That's fine, but the direction of force will be different. Suppose I assume this is electric field. Okay, so the force on proton will be same. Force on electron will be opposite. Okay.
So proton will move faster than the electron because electron is experiencing deceleration when the proton is experiencing acceleration.
No, but it's just moving in the opposite direction, but the distance traveled will be same, right? Could be same. So what about this? What about the value of the force? Is it same?
Sorry, what, sir?
Magnitude of the force, is it same?
Yes, sir.
The magnitude of force on the proton, it's E into E, right? And magnitude of force in the electron is also E into E. Force is same. What about acceleration of proton?
E by T.
Is it same?
T1.
By what?
T1.
Acceleration is what? Force by?
Mass or MP.
Okay. So this is E by ME. So which one is more?
Acceleration of the electron is more.
Okay. So the time taken, how will you find that?
V by A.
Is this true? Is equal to half AT square?
Yes, sir.
Why is it true?
Because constant acceleration, no, it's not a varying electric field, uniform electric field.
This is UT plus half AT square, no?
Yes, sir.
Then what happened to UT?
Root 2 S by A.
What happened to U? That term is gone.
Initially at rest, they have given no, sir.
Okay, fine. That you have to say no. So time is 2s by root A. So time will, this is same for both. Time will go as square root of A, right? Inversely. So T2 by T1. Since the ratio will go as A1 by A2. Okay.
MP by M. Option D.
Electron is 1, right?
T2 by T1. Okay, not T1 by T2. In option C.
P by M. Okay, option B is the correct one.
Yes, sir.
Okay, suppose this is in but suppose this I'm dropping this is Earth's surface. I'm dropping this electron and the proton. Okay, then what will be the time taken? For both, will it be same or different?
Different only, sir.
Why? It's falling
Why?
under gravity. Okay.
E is it says horizontal direction or what?
Earth means it will fall vertically, no?
Okay, vertically.
Earth is down. I'm dropping electron and proton from a height. Okay. So what is the time taken for it to reach the Earth? Both of them, will it be same?
No.
Okay, suppose I take a mass M and a bigger mass capital M and drop it on Earth. Will it take the same time to reach?
Proton will take lesser time, sir.
What about acceleration of both of them? Will it be same or different?
Different.
Why is the acceleration different?
Mass different. They have same mass and they left.
Acceleration for both it is G, no?
Oh, okay, okay. Sorry. Fine.
This is the famous Galileo.
They both fall at same time, sir.
Yeah. So T1 equal to T2 here. Okay. So to understand why the acceleration is same for both, acceleration of one is force on one, that is mass of electron into the G divided by mass of electron. And acceleration of
No, but you didn't consider that the electric force, sir. E plus.
No, there is no, just gravity.
You said that electric field is also vertically present over there.
No, what is there? That's a problem. Okay, so only gravity present means both will reach. Acceleration is same for both.
Okay, fine.
we will stop now. So,
Okay.
so when I'm going to revise these first 6 questions, if you don't revise, you will forget. So tomorrow morning,
The
because
sun.
no, not. You have to revise the next day, otherwise you will forget. You have to revise.
Okay, today's topic as well.
Whatever I teach today, you should revise the next day. Okay, and then second division can be after the third division. I'll send this GNT file. Those 6 questions you should solve tomorrow without looking at the solution.
Yes, sir.
Solve 6 questions at a stretch. Don't look at the answer. And after you mark the answers, and then after taking the 6 questions, you check the answer. Okay.
Yes,
Okay, we'll stop now.
thank you, sir.